Propulsion is generated from the equal and opposite force of the acceleration of water through the nozzle due to the energy provided by the compressed air. The water fraction can vary, which leads to differing amount of impulse and thrust. Impulse is a term that quantifies the overall effect of a force acting over a time, found by multiplying force by time. Therefore, we have to decide using simulation and spreadsheet analysis which water fraction would generate an appropriate amount of thrust over time while not making the rocket too heavy. For the rocket to be directionally stable, when acted upon by a rotational disturbance, such as wind, a restoring moment must be generated, returning the rocket to its original direction of motion, allowing the rocket to fly straight. The fins act as a lifting surface, which helps to provide a restoring moment to counteract the pitching up moment of the rocket body and nose cone about the center of pressure. Placing the fins at the bottom of the rocket increases stability by moving the center of pressure further after the center of gravity, providing a greater restoring moment, allowing the nose cone to realign with the velocity vector. Increasing the fin area also increases directional stability, as it causes the center of pressure to also move further after the center of gravity. However, by increasing the fin area over a certain point, the restoring moment will become too large, making the rocket directionally unstable. Increasing the parachute diameter reduces the terminal velocity for a falling object. Terminal velocity is the velocity reached by a falling object that experiences zero acceleration. This occurs when the upward drag force acting on the rocket due to the parachute becomes equal and opposite to the rocket's weight. A larger diameter parachute, hence one with a larger area, generates a larger drag force, meaning that the falling object will undergo less acceleration due to its own weight before the drag force becomes equal to the weight. However, a larger diameter parachute will increase the weight of the rocket as well as taking longer to be deployed from the rocket. Both of these can lead to a greater terminal velocity. By looking at each different aspect of the rocket separately, we can optimize each part for the best performance. Some aspects require us to find a balance, like the water fraction, where too much will make the rocket too heavy and not enough will generate very little thrust. Other aspects require simple maximization. However, no matter how perfect the theory is, there will always be practical difficulties. Build quality was another parameter in the simulation that affected rocket performance. Varying values were tested as this quantity could not be predicted. Furthermore, another thing we can't predict is the weather. Launch conditions can vary greatly, and it's impossible to predict and prepare for every outcome. The performance of the rocket is inevitably going to decrease with poor weather conditions. We've learned a lot throughout this project. Integrating technologies such as Unity and Excel into the designing process allowed us to streamline the process of optimizing design parameters for the rocket. We learned the importance of 3D CAD software to visualize the design of the rocket before building it. And we also learned that some factors impacting the performance of the rocket can't be predicted, such as build quality and the weather.